Dr. Manoj Varman. His paper is on stronger SSRs through evidence-based strata control, lessons from underground coal case studies.
Thank you, Mr. Chairman. My name is Manoj Varman, and I represent this company, Rocscience, which is into geotechnical software for mining and civil engineering, being extensively used around the world, including India. And you can see the topic on your screen, but what is important about is a good old SSR it is talking about, which comes from DGMS. But then, when we talk about mechanization, when we talk about mass production, when we talk about achieving 100 million tons by 2030, which means we are talking about increasing production, scaling up, ramping it up massively from underground coal. Now, to do that, we need to have a relook at the SSRs which as they exist today. And this is what it is. And to do that, I'm going to propose an approach where we use numerical modeling to strengthen the SSRs. There's a little problem with numerical modeling, and I'll try to explain that. I'll be brief, I'll skip. So, the numerical modeling is generally seen by the industry as alien. You know, you bring forward colorful printouts, and most people don't understand that. It is not generating much confidence. So we really need to link that numerical modeling to the daily decisions that you take in mine, you know, for pillar geometry, extraction limits, support density, junction treatment. And that's what this paper or this presentation aims to do. What I'm trying to emphasize on is that you can bring in any amount of mechanization and you can bring in the technology, which is extremely a welcome sign, but then there's a thing called strata control which can limit the usage of those technologies, because in practice the productivity that we are talking about since yesterday may be constrained by examples are gate roadway deterioration, for example, near advancing Gulf, unexpected convergence, unexpected sidewall behavior which could compromise the transportation and ventilation, for example. So strata control is the key really if you really want to sort of achieve the mechanization and achieve the mass production that we are talking about. Because in addition there could be other bottlenecks, like people talked about chain pillars or barrier pillars, particularly under abutment loads, also the roof fall sensitivity, all those things. You know, the intersections, the junctions behavior, all those things can put a limit to the mechanization. And these are precisely the locations or situations where the SSRs as they exist today need to move beyond the static SSR that we have, and they have to move to what is called the risk-based zoning, and I'll try to explain in next 5-7 minutes. To achieve this, what we have done is, Rocscience has published several case studies from around the world. So I have tried to synthesize 3 of those cases from underground coal from around the world to see if we can learn something. And the objective is to translate these cases to practical recommendations to strengthen the SSRs. And the focus areas are, as you can see, pillar performance and extraction strategy, the roadway behavior and support zoning near abutment, intersection junction stability in jointed roof. So outcome expected is a simple implementable framework which complements the Indian empirical practice. You know, we use a lot of empirical formulae, we use analytical methods for design of underground mines, and so that practice has to be supported. And also this approach will support the DGMS facing submissions and approvals, which is so crucial. But before I go to those 3 case studies, very, very quickly, I'll take a minute each for those. In those case studies, these 3 or 4 software tools from Rocscience were used. RS2 and RS3 are based on finite element method, and you can model anything using finite element method, 2-dimensional, 3-dimensional. And also, there are situations in underground structure where it is not always that the instability is because of the stress-induced instability. It could be controlled by the geological features, the discontinuities, in which the blocks and wedges which are formed because of intersection of these discontinuities can fall or slide into your underground excavation. So those things. There are different mechanisms, different software tools for those. So 2D and 3D finite element method and 2D and 3D limit equilibrium kinematic analysis kind of thing. Anyway, so I'll skip some of the slides. So let's come to the case study number 1, which is from Greece, an underground mine, moving from open pit to underground. And there was a pilot project initiated consisting of 9 pillars. As you can see, there are access tunnels, there are cross cuts, there are parallel roads, forming about 9 pillars, which was modeled in the software RS3, which is 3-dimensional finite element model. And I'll tell you the beauty in a moment. At the actual ground, when you sort of develop an underground bord and pillar, for instance, you do not do it in one go. You do it in stages, gradually, bit by bit. So all those stages can be modeled in the software, exactly as you would do. Not just the geometry, but the excavation sequence, the staged excavation, the stress conditions, the groundwater condition, anything which is going to govern how the mine will behave can be simulated on your computer screen, and that's what was done. And you can see it required 84 stages in the model to reach the finally develop this pilot project. And so these are results can be in the form of deformation, convergence, stresses, anything. So this is displacement contours shown, or deformation contours shown, and you can see that, you don't have to really be worried about the values, they are given in the legend, that the predicted maximum displacement from the analysis was about 50 to 70 millimeter in the central room area and about 40 millimeter near the main axis in back of the mine. And you can see they're not uniform. When they were measured, they matched very well with the measured values. And also in the pillars about 15 mm, and the pillars bulged in 3 axes. So the important thing is that it was not uniform. So from this case study, you had a design to field proof through staged modeling, staged 3D modeling, and which can validate the pillar/support strategy before you scale up the operations. And there was a clear linkage of the predicted trends matched with the observed behavior supports. So they were not just academic add-on tools. Industry thinks they are just academic, because academician, and there are some here, we present it that way. We have to talk in the language the industry understands, and then you see the change happening. So what is the linkage to SSR? Linkage to SSR is use 3D validation triggers for bigger panels, critical barrier rules, complex junction. You can link the reinforcement density of roof bolts, for example, to the stability confidence, and that is where the SSR can be improved. Second one is a case study where TAT, which is very prevalent analytical method for room and pillar, board and pillar, tributary area theory for assessing the stress, and it is well known now through researches that TAT, tributary area theory, either overpredicts or underpredicts the stresses, which can either lead to overly conservative pillars, which mean you're losing productivity, or unsafe or under-designed thing. But this case studies used a combination of 2-dimensional, 3-dimensional finite element modeling, and found that this TAT actually usually overpredicts, and therefore you're losing productivity. And these are the things you can see, those blue lines, solid one and dashed one, at different depths of the mine, clearly overpredicted the stresses. The stresses were much lower than that, and if you had designed with those lower stresses, you could have produced more coal out of those locked up pillars. So this combined thing, and also looked at 2 dominant pillars geometries, rib pillars and square pillars, and it was found that which of the approach suits what kind of pillar. And so new formulae were developed based on this, which are very close. The TAT can overestimate up to 2.5 times, but then those formulae predicted stresses which were very close to the actual ones there. And these are those colorful things I was talking about. So key lessons from this is that you get a pragmatic bridge. You can upgrade the stress screening accuracy without requiring 3D modeling. And I'll come back to that a little later when I conclude. And this approach helps manage what is now familiar, that you can retain your safety margins while avoiding the avoidable loss of recovery. And that's the beauty of it, which comes from overestimated stresses. And different pillar aspect ratios, rib and square pillars, need different treatment. And the SSR linkage of this result is that you can keep the empirical approaches, you can keep the analytical approach of TAT as your baseline. Don't disturb that. But adopt improved formula or targeted 2-dimensional, 3D analysis when things change. For example, when extraction ratio goes up, when panel width goes up, when the chain or barrier pillars are critical, or the mine depth is increasing. So those are the areas where you step in with these advanced things without disturbing the baseline. And the third one is about the horizontal stress. I'll be very brief because we're running out of time now. See, stresses play a dominant role. Many of us realize this, many of us do not realize this. And when I say stresses, it's not only the magnitude, but the direction also. Like there was this study carried out, and it was found that when the roadways are perpendicular to the major principal stresses, you get the maximum instability. When it is parallel to it, you get the least instability, but it could be at any angle. So all those angles you can do when you create the model, and which was done in this case. And this actually is cases from UK and our own Singrini, VK7. And so the results, I'll go to the results straight away.
Mr. Manoj, please conclude.
Just 2 minutes. Yeah. So those are the results, basically talking about the stresses and how stresses, magnitude and direction play a role. And when we are trying to move underground deeper and deeper, the stresses are going to increase. Vertical stress is going to increase. The ratio between horizontal and vertical stresses and the direction is going to be crucial. Despite any mechanization, this is going to be a huge parameter to consider. I can tell you that. And so these are the results matched very well. So finally, before I conclude, these are the 6 steps which we suggest for DGMS, for the industry to follow. These steps are DGMS aligned, and this workflow, step 1, keep the baseline intact with whatever we are doing, empirical formulae, the legacy norms, the etc. But the step 2, first line screen could be done by simplified analytical checks, and then you move to 2-dimensional analysis, you move to 3-dimensional analysis when the conditions are difficult or challenging in those cases, and then link those to SSR zoning. So I will conclude by saying it can't be one size fit all. You can have standard zones based on the existing SSR, but then you can have risk-based zoning for more challenging areas based on 2-dimensional and wherever required 3-dimensional analysis. So I'll conclude with this. So couldn't discuss more, but anybody who's interested can go through the paper, and we are always available for any discussions. Thank you very much.
Any questions, please?
Good afternoon, sir. I love to ask a question because you are a renowned geotechnical engineer and you are also visited many places, many countries. So, in underground coal mine, it is not always drive a gallery parallel to the direction of the major horizontal stress. So, what should be the minimum angle for the development of the cross cut?
That is so site specific. You really need to answer that question, you really need to measure the stresses and the magnitude and the direction. So to answer the question, the direction is not always in your control, right? So if you change the direction of this, if it's a sort of perpendicular to each other, the other direction may become critical. So more than that, it is important to know that if you're trying to avoid a major geological discontinuity or a feature like a fault zone, etc., then I can understand. But this angle is something that you can avoid for some roadways, you can avoid for other roadways. And therefore there's an importance of designing differently for different underground structures in the same mine, based on whatever angle you have and whatever magnitude you have.
Okay. So one more question, sorry. Hidden slip is the biggest enemy for mining engineer.
What?
Hidden slip, hidden weak planing, hidden geological discontinuity.
Yeah. Weak planes.
Have you any technology to detect in advance so that we can take a precautionary measures?
Yes, in fact, Dr. Veera Reddy mentioned it and Sir mentioned it, that you have to carry out geophysical techniques in advance, and which can give you ideas about that there could be some problem here, there could be hidden weak planes of weakness here, and then you have to, based on the geophysical results, you have targeted boreholes to do that, because putting borehole recklessly is not the answer. And those boreholes may not always be vertical, they can be horizontal, they can be done from inside. So those things are available, but you must have the first idea through a non-invasive technique involving geophysical things. Right, thank you.
Dr. Manoj Varman is on a stage. I request the chairman, co-chairman and rapporteur all together to present मेमेंटो। मैं आप सभी से निवेदन करता हूं जोरदार तालियों से लर्निंग फ्रॉम द पास्ट के फर्स्ट सेशन के लिए